So pretty much I'm going to cover CPUs, GPUs, FPGAs, and I'm also going to give a very small taste of ASIC, okay? Right, so Omer at the beginning of the day said that CPUs is not the right device to run zero-knowledge proofs, and I'm not going to contradict that, but I do want to give it a fair chance. So given that we're mostly been talking about a beast of a GPU, I also want to bring out a beast of a CPU. So let's go. So this is the newest AMD Genoa CPU, which is released, I believe, earlier this year, or maybe Q4 last year. And it's got 96 cores at 3.6 gigahertz. Okay, so and bear in mind that this talk is going to have a few of these silicon images. So the CPU has, in fact, it has many silicon dies. So it has 12 of these compute dies. Each die has 8 cores each, and you can see them here, right? And it has this in the middle, which is the I/O die, which handles the PCIe and all the memory controllers and stuff. So this is pretty much the highest range CPU that you could buy in a server right now, but there are actually even bigger ones. Recently there was 128 cores released. Next year will be 256 cores. We have 12 of these silicon dies, and each of those look like this. They're 70 square millimeters, and you have 8 cores each on the sides. Does anyone want to guess what is in the middle? Cache. Yeah, this in the middle, which takes about 50% of the silicon die, is L3 cache. And only on the sides you have the cores. So each of the cores is actually 3.85 millimeters squared. And does anyone want to take a guess at how much silicon area is actually dedicated to, forget integer performance, let's just say performance like computation, as in multiplication, addition, subtraction, division?
5%.
5%? Anyone else? Okay, you're correct, 5%. Yeah. So only this part, integer execution, and this part, the floating point units are actually the subtraction, multiplication, and so on.
Does that include vector units?
Yes, I will touch on that. So yes, the vector units on this particular chip is actually a part of the floating point silicon. So yeah, most of the chip is either cache or more cache or load store scheduling, branch prediction, which is fairly special to CPUs, and out of order execution and so on. So this diagram is actually what was the abstract view of what was on the previous slide. So a CPU is a very complicated machine, and it's got a lot of moving parts. So it's very complex. It's so-called superscalar, which means that it's able to execute more than one instruction every clock. In fact, here you can see 1, 2, 3, 4 integer ALUs on this one core. So you can actually execute 4 integer operations per clock, theoretically. It's also out of order, which means that the program that compiles, you get the binary code. That binary code is not executed line by line. It's actually, the CPU actually can reorder your instructions, it can fuse instructions, it can split instructions. So benchmarking based on what the lines of assembly you get is not a good way of benchmarking on a CPU. Well, it won't tell you that much, other than is it fast or not. Yes, in this CPU, the Genoa CPU, there's 96 of these, but it ranges from like 16 core to 128 cores right now. And depending on what CPUs you get, so like on the lower range, like with less cores, you get higher clocks. On the upper range, you get a bit lower clocks, but more throughput. So interesting thing to note here is that your instructions that you compile, x86 instructions that is part of the instruction set, that's not the instructions that are executed. So x86 is just a specification for which your compiled code is like kind of guaranteed to be compatible with all the vendor CPUs. But each vendor, like AMD, Intel, well, those are the only ones that make x86 CPUs, but they both have very different architectures. This looks very different. So expecting the same code to run like efficiently on both vendors is not necessarily a good assumption either. And the x86 instructions are broken down into micro-ops, which are like what's actually executed on the CPU. And, oh, no. Okay. So the x86 instructions are actually decoded up in this front end here into micro-ops. And there's multiple micro-ops that can flow down into this execution pipeline. So, for example, you can have one instruction that produces two micro-ops that gets executed on two ALUs in the same clock. And a note about the vector instruction is that on this processor, it's actually done like for the integer vector operations. The integer vector multiplier is actually done on the floating point. And we'll see an interesting thing in the next slide. So on CPUs, there's actually kind of two ways of, like two different types of programming paradigms. So there's one way, the normal way, which is the scalar program. So that's where you have like your C code where you do your times operator and so on in a sequence. So that gets translated into like a multiplication instruction, mul, and you can have multiple threads, up to 2 physical threads running concurrently. But technically, you can actually, in the same thread, run multiple instructions in parallel. So you could potentially have 2 multiplications in parallel, as long as they don't depend on each other in a single thread. And for this CPU, there's 2 physical threads, and so you don't want to go more than, if you want to run instructions back to back, you don't want to go more than 2 threads. Otherwise, you'll pay a software penalty for switching threads. And the other way is so-called SIMD, which is single instruction, multiple data, which means that we issue a single x86 instruction, but it operates on multiple registers. Well, multiple pieces of data in the single vector register. Okay, so in this case, we have the VP MAD instruction, which is 52 bits, takes 2 52-bit operands, multiplies them, accumulates them, and gives you, and can either select to get the high or low parts of it. Right? So it's similar to the GPU. but the downside of SIMD, unlike a GPU, whereas GPU is SIMT, where single instruction, multiple threads. This is single instruction, multiple data, which means this instruction has to happen on the same thread. But you have to kind of organize the data before you call this. Whereas on the GPU, you can sort of write a program that looks like multiple scalar programs. So I'm going to use a weird metric here, where in order to compare multiple architectures, I'm going to use so-called bits of work, which really means I'm really comparing the multiplication here, the multiplication operator. And bits of work is really just the operands squared. So if it's 64 by 64, then it's 64 squared. And using that, we can calculate how many bits of work we can do per clock, basically. And an interesting thing is that the scalar instructions and the SIMD instructions can also be in parallel, as long as there's enough ports for the micro-ops to flow through the pipeline. So actually, you can do 8K bits of work here, 10K bits of work here. In order to get to get both of these working at the same time is a nightmare, because you're writing two sort of different programming paradigms in the same code. Okay, let's move to GPU. So this is the GA102. So this is the Ampere series 3090 Ti.
I'm sorry, can I ask a question on the previous slide?
Go on.
So that 10,000 bits, how do you come up with that number? That's 52 times 52 times 8?
52 times 52 times 8, yes. No, 52 times 52 times 8 divided by 2, because we're...
Low and high.
Yeah, low and high.
Okay. Got it.
So next let's look at the GPU. This is 3090 Ti. And the GPU is organized into like many levels of hierarchy. So this is kind of the picture of the entire GPU. And it's organized into these things called GPCs, which are graphics processing clusters. And each GPC in this architecture has 12 streaming multiprocessors, SMs. And the difference between like the GPU models usually comes down to how many GPCs they include in the die, or how many they let you use. Okay, so in each SM with the Ampere series, you actually have 4 sort of real cores inside each SM, whereas NVIDIA likes to advertise that they have like 10,000 CUDA core or something. They're not really full cores. They're more like ALUs. So you can see you have inside each SM, you have like these little elements where each one has its own scheduler, its own register file, its own load store units, and so on. And in terms of processing, in terms of ALUs, you have 16 integer, you have 32 floating point 32 units, but only half of which can be used for int32. That's kind of where, Dima talked about with the heavy and the light pipelines. So this one that can do both FP32 and int32 is the heavy pipeline. So yeah, each processing element has a register file that's actually quite big, 16K entries, which allows it to hold many thread contexts. So yeah, in each processing element, you can dispatch 32 threads per clock, so that's called a warp. But if we're talking about integer performance, then really only 16 threads can run at a time. In NVIDIA documentation, they usually talk about multiplication taking 2 clocks for the half multiplication, or 4 clocks with the wide multiplication. That's kind of where it's derived from. The multiplication physically takes 1 clock, but it only executes on half the ALUs. So the throughput is like 2 clocks based on the number of cores you have. So correct me if I'm wrong.
I think that's not right. I think what happens is that it's every 2 cycles you can push another thing into the pipeline.
Okay.
But I think that it's actually, because I know you can launch an FP and you can launch an ALU 1 cycle apart. So that can be right about it doing half. We can talk about it all.
Okay. Okay, so with the L1 cache, you get 128 KBs used as cache for global memory, but you can also assign a portion of it to be used as shared memory. Is that right? Yes. So not all of that cache can be used as shared memory. There's specific configurations that you can select. And the access granularity on the cache is 32 bytes for L1. So with GPUs, you have single instruction multiple threads, which is a bit easier to deal with than SIMD, because now each thread can keep its own context, which means that they can be sort of at a different part of the program at the same time, although you don't necessarily want to do that because it has some performance penalties. Yes, so in terms of bits of work per clock, I calculated as 32K bits of work, which is 4 warps times 16 threads times the number of work per multiplication per SM. So here's another pretty picture. So this is the J0102. This is the 3090 Ti. So as you can see, there's still quite a lot of other things on the on the chip. So mostly memory controllers and again L2. So you can see here we have 7 GPCs. Inside each, you can kind of 6. Maybe that's might be a different chip, but okay, yeah, 6.
Is this how it looks also in the 3090? Like the previous diagram is not this is the actual layout, right?
As far as I know, 3090. Oh, this is 3090, I think. The other one's 3090 Ti. I'm not exactly sure, but it says GA102 here, so I don't know. So you can kind of see that there is SMs here, like line by line, and probably the middle is cache. I don't know, but okay. Per GPC is about 50 millimeters square.
Just dive into what is TPC?
It's a processing cluster, so it's each GPC has 12 SMs.
Which one?
The left one.
The TPC?
No, yes, exactly. Sorry, yes, that's the 7th. So inside, it's yeah, it looks like that. And TPC is another layer of abstraction. Yeah, hierarchy.
Connie,
Hmm?
how does the numbers add up in terms of area? Because I see 50 millimeters squared
Mm-hmm.
and times like
7.
7 or 6, it doesn't get to 628.
Yeah, that's because only about half the die is the GPCs. So here you can see GDDR6 so that's the memory controllers. Okay, that's all around here. You have L2. On the 40 series, there's a lot more L2. What else we have? Yeah, PCIe controller, display, MV. Yeah. Yeah, because remember this is a graphics processing unit, so it's daytime. Well, depending on which field you're in, the daytime role is display and 3D rendering. So that's GPUs. Now let's go to FPGAs. So FPGA is a bit different, where we don't have like large processing units to kind of count. But what we do have is what's called lookup tables, which are, here we have a 6-input lookup table, which you can think of as kind of like a memory, like a small ROM, I guess, where you have, like, you can select an address with these input bits and then to get the bit stored in memory of that address. So with this, you can actually implement like any sort of 6-input truth table, right? So that allows you to implement Boolean functions. You also have flip-flops, which captures a bit of memory, like a state, like register, 1-bit registers. You have DSPs, which are used for implementing like the multiplication, so you don't really want to use lookup tables to implement multiplication because it's really inefficient. Yeah. So you have these hardened multipliers.
Most of the time it's inefficient. Sometimes
yeah, it depends.
It would be
It depends. Traditional school book sort of, yeah. You have also small memories called BRAM, block RAMs. They're like, think of several kilobytes of size, kilobits of size. And you have these groupings called CLBs, configurable logic blocks, which group many lookup tables and many flip-flops into the one sort of unit, so we can, the silicon designers can actually easily plop them down into the chip. So yeah, a full FPGA looks something like that. I mean, there's going to be way more of these, but you have like a sea of these, and then you can kind of choose to wire them however you choose. However, there is a little caveat in that routing, like the switches that can route this CLB over to say this VRAM, that's actually limited. So it's not technically right that you can route it whatever you choose, but. So one chip from AMD is, like an example FPGA is VP1502. It's got 1.7 million lookup tables, and you can arrange them to sort of build Boolean, or anything really. For example, it's very efficient at implementing hash functions like catch-hack and so on. You also have 7,000, a bit more than 7,000 DSPs. Each DSP implements a 24 by 24 multiplier. 24 by 24 equals 58 bit. I know, 48 bit. 48 bit.
23 by 10 is 7, right?
Yeah, I'm just discounting that. Yeah, it's technically 24 by 28. Yeah, but signed.
So
Yeah, but I'm just going to count it as square.
24 by 24 is unsigned.
Yeah.
You can do unsigned.
Yeah, so which gives us 576 bits of work per clock, okay, on each DSP.
Are you going to normalize those bit of works to the frequency?
Yes. So recent development is that FPGAs, they're also getting sort of these fixed function processors attached onto them. So one example here is FPGA plus AI engines, which is a new product from AMD. And these AI engines are kind of like an array of processors, processors. There's actually 304 of them in this array. And the cool thing about this is that data kind of flows from one engine to another through these memories. So each engine can actually reach out and can pull memory from its neighbors. So in like a mesh, yeah, exactly. Or it can transmit through like this sort of packet switch network. And each engine has both a scalar unit and a vector unit. It's very, very similar to GPUs in that sense. Except the vector unit is SIMD. So if we're only counting the vector unit, then each vector unit has a 16-lane 32 by 32 equals 64-bit multiplier. And it runs at 1.25 gigahertz, so a bit slower than GPUs. So that gives us 16K bits of work per engine per clock.
So for the routing network, is it seamless where, are there like different instructions to say get something from my neighbor or get it through the routing network? Do you have to know?
Yes, yes, there is.
Different instructions.
It's a different instructions, yeah. And the way that they envision you working with this is that you would have like double buffers on each of these memories, and one would write to one buffer and the other one will pull from it, and then they will switch, they will
And
swap.
then you send like a signal to
Yeah.
it saying, hey, I'm
Yeah,
done.
yeah.
So there's some consumer producer model.
Yeah, yeah.
for
But it's
something.
handled in hardware. Yeah. So, this is based off the bits of work for integer multiplier. So I understand that a lot of times you want to multiply add, but we're just comparing multiply here. I mean, so a lot of the previous numbers are actually multiply add, but let's just ignore the addition part for now. And so what's perhaps surprising is that the CPU is actually pretty good in like theoretical performance. I'm not saying that you can reach this easily, or even possibly, maybe it's even possible to reach, but
But in that number, you're including vector and
yeah, well, both vector and scalar.
right
Yes.
every cycle.
Yes. Yes. So yeah, it's actually better than the 3090 Ti, but bear in mind that the 3090 Ti is a lot cheaper than that CPU. If you compare like the A100, H100, that's a different story. But of course, 4090 still takes the crown here. And the FPGA is kind of lagging behind. The pure FPGA is kind of lagging behind worse than the 3090 Ti. But bear in mind that this one is still, I'm basically counting just schoolbook multiplication. So if you want to build multi-precision, sorry, not multi-precision, you want to build larger multipliers, you can employ caret super in a very efficient way on the FPGA. Yeah.
This is not. This is just per clock, right? It's not.
No, this is scaled. Sorry, this is scaled to the maximum frequency of each device. Yeah.
In VP and VC, you're counting both AI engines and DSP blocks?
Yes, but the DSP blocks for the VC, this one, which is including the AI engines, is like 10%. So it's like
So
mostly,
this is
yeah, mostly from the AI
VP
engines.
is the premium? That's the
Yes.
one that only has the DSP blocks?
Yes, yes. So in terms of like silicon area, the VP is like similar in size to 3090, and the VC is actually smaller.
Can
Yeah.
I for mention this? So you're
Yes.
not counting the tensor cores on the
Yes.
GPU.
Yes.
The tensor cores actually can do more integer math, but they're hard to use.
Right. Yeah. That would be, I think.
Tends to use them.
I think that's a workshop item, right?
I've written some code to actually do that.
Okay, that would be very interesting. I haven't really considered using the.
Interested in
Yeah.
stuff on the tensor cores.
Okay, cool.
Doesn't work very well.
Okay, so finally, I just want to give you like a tiny taste of ASIC. And bear in mind that this is like Um, 3 hours of work, of which 2 hours and 30 minutes are of compile time. So don't take this as like the limit of what we can do. So this is a 377-bit modular multiplier, fully pipelined, 500 megahertz, uses 1 watt, and consumes 0.233 millimeters squared. And this
Gross, with the unused packs.
yeah, there's also some unused parts you can see. So with this sort of size, you can like feasibly have hundreds of these. Of course, this doesn't. this is just a multiplier, and it's not doesn't have like any of the memories that you would need and control logic. But of course, 7 nanometer. Yeah. Yeah.
500 is very low.
Yeah. I mean, this is taking our FPGA code without any modifications, running it through the compiler, and that's it. I didn't touch anything. Yes.
I think the main thing to note, this is the code that the Verilog.
Yeah.
Really the Verilog that we use in the FPGA that is optimized
For FPGA.
Ultra Scale Plus.
Yeah.
Okay. Obviously, when we write dedicated silicon, we're not going to do the Karatsuba the same way. I mean,
Yeah. This is the result of, like, minus the development time for the original FPGA code, this is like the work of 30 minutes. So, like, just keep that in mind. Yeah. Okay. So, yeah, that's the final slide. So I hear,
Sorry,
yeah?
Where would you put that on that previous graph? So was it there?
how many bits of work is it?
Yeah.
Well, let's see. No, 3. Anyone got a calculator?
Is it just that simply just multiply?
Yeah. It's modular. So let's say
It's a modular
times 2.
multiplier.
Yeah. And this has also got some Karatsuba.
So let's say it's
I mean, let's take the area.
let's say it's a
Okay.
gigahertz.
Let's take. You had 628 millimeters in 4090.
I think it'll melt the chip, but
No, hang on. Let's say that we only gave like 100
okay.
millimeters squared for these.
Okay, you just take this
So how many
squared,
did you get?
okay, times 2 for
So
modular
you get
multiplication.
500. If you gave 100 millimeters squared, you get 500 of these or 400 of these.
Yeah.
Okay, so 400 watts, which won't melt the chip.
Yeah, that would be
You
similar to
spread
the
them
3090, yeah, right?
So you get 400 watts.
Yeah, but okay, hold on. We also have to count in the things that do take a lot of memory, take a lot of power, which is the memory and stuff. But let's say compute. Let's say 200.
I think it does take into account the interface. And the memory itself doesn't take that much power. It's the interface.
Right. Yeah. The phi and all that. Yeah. Well, let's say 200 even.
Let's
yeah.
say 200.
Yeah.
So how 200 of these? 200 times. It's 100.
This is enormously fast.
Yeah.
Yeah. So this is like a taster of what an ASIC could do. I mean, if
100
it, yeah.
gigamoles, but already modular.
Yeah.
Right.
Yeah.
But also very dedicated.
Yes.
For this.
Yes. And also, this is
I
take.
think the
Yeah.
most important thing that you need to understand about ASIC is that you build it ad hoc. Okay, let's say you're building an ASIC for MSM. Okay, so the utilization will be almost 100%. Okay, and this is the major power of ASIC. Regardless the numbers that Tony mentioned, and he was quite correct. ASIC is dedicated. Okay. And once you're building it dedicated, then everything is going to work. Okay, the GPU is, if you're at 60% and you're extremely, it will be extremely efficient, right? FPGA, we're at, I think we're at 20%, and we are.
Yeah, of course. Another thing to mention is all the different silicon I mentioned, they have different development difficulties that I didn't mention, but it's. Yeah, we have to. I think the GPU takes the crown in ease of development, better than CPUs, at least based on what I calculated in terms of performance.
program.
Yeah, but in order to use SIMD, both SIMD and the scalar, that's
Right, to hit that.
yeah. Yeah. So, any last questions?
That was a